What's up, sports fans? Here we go with trigonometry team test. I'm going to do every problem, every piece of every problem. Feel free to pause, rewind, whatever it is you need to do to make sure we understand these problems. These problems here are basically what you're going to see on the test, the formatting, all the things. You can see here I have a bunch of triangles I'm asking you to solve for missing pieces of. You need to determine which tool you're going to use. So for these, I'm looking for sine, cosine, tangent, or inverse sine, inverse cosine, inverse tangent. Other options are Pythagorean theorem. Another option would be 45, 45, 90 special right triangles or 30, 60, 90 special right triangles. So I'm going to talk through all these. I'm going to point you to where you can find different things in your notes at different points. The aim here is just to give you all the information, all the tools to equip you to be all super successful on this test. Here we go, part A. We are trying to solve for x. We know this 62-degree angle, so we are going to view the triangle from this 62-degree angle. From this perspective, the x is the adjacent leg, and the 22 is the hypotenuse. So reminding ourselves about SOHCAHTOA, which we should write on top of every time we ever do trig. We should write that at the top so we have that as a reference. I have an A, I have an H, that's going to be cosine. So I'm going to set this thing up and say the cosine ratio from the perspective of the 62-degree angle, or we can say cosine of 62 equals the adjacent leg over the hypotenuse. The adjacent leg is x, the hypotenuse is 22 degrees. So remember, that's the big part of this problem. That's basically 3/4 of the credit for this particular problem. The remainder that I'm about to show you is how to get the, basically that last point out of 4. Because this is the trig. We've done the trigonometry. The next step here is going to be the algebra. So I'm trying to get this x by itself. Right now it's being divided by 22. So I'm going to undo that division, and we undo division by multiplication. So now we have 22 times the cosine of 62, which again is just some number, equals x. Now we've got x by itself. It's time to press buttons on our calculator. So I'm going to type it just like I see it. 22 times the cosine of 62 degrees, close that parenthesis, click equals, and I find that that value is approximately 10.33. So notice it's 10.32, but this 8 right after the 2 is 5 or larger, which rounds this value up, so 10.33. Now, one quick verification, let's make sure that makes sense. First of all, is it positive? All these lengths must be positive. It is. Cool. The second thing we need to look at is 10.33 in the same ballpark as the rest of the information that we know about this particular problem. Well, we know we have a hypotenuse of 22, length of 22 units, and the hypotenuse must be the longest of the 3 sides. Well, 10 is shorter than 22, and it's, generally in the same ballpark. If the short leg is 10.3 and the hypotenuse is 22, yeah, that's reasonable to me. So I'm going to move forward as though we got what we needed here. So 10.33, I'm going to put my final response right up here. And the tool that I used, this is essential, this is something I'm 100% grading, is that you need to put that you used cosine. You can just abbreviate it as cos. You can write out the whole ratio. I'm happy either way. Okay, I'm going to pick up the pace a little bit here. Part B, I don't have any angle measures other than the right angle, but I do have 2 sides. The move that we're about to do is a pretty simple one, but the hard part is identifying which tool do we actually use, because we're so used to like, oh yeah, it's definitely trig. So which angle do I view it from? I don't know. I don't have any of them. Well, remember the easiest tool out of all of them. It's Pythagorean theorem. We have 2 of the leg lengths, and we just want the hypotenuse. So it's a squared plus b squared equals c squared. Remember, a and b doesn't matter which one's which, as long as the hypotenuse or the longest side is your c. So I'm going to set this up as 3 squared plus 6 squared equals x squared. Let's simplify and see what happens. 3 squared is 9, 6 squared is 36, and x squared is x squared. Let's add 9 and 36 to find that x squared equals 45. Now we find the square root of both sides. The reason we do this is because we're trying to undo the square that's being done to the x. The inverse operation is square rooting. So on the right-hand side, we get our x. I'm taking this over here. The square root of 45, however, well, that's not a perfect square. So let's ask our calculator. The square root of 45, oops, didn't need that extra parenthesis, 6.71. Remember, again, 8 rounds up this number here. So 6.71, and this should be an approximate here, 6.71. Again, make sure it makes sense. We're trying to find the length of the hypotenuse, so it needs to be the biggest and it needs to be in the same ballpark. 6.71 is bigger than 6, and yep, that makes sense to me. If we ended up with a number like 100, that wouldn't make sense. You're not going to have a triangle with side lengths of 3, 6, and 100, so it needs to be in the same ballpark, which this one is. Now, what tool did we use here? We used the Pythagorean theorem. Don't worry about memorizing how to spell. I mean, it's in your notes, so hopefully you spell it correctly just by looking there. But somehow communicate to me that you're using Pythagorean theorem. Even if you just write Pythag, I'm okay with that. I know what you're trying to say. Heck, if you just write a squared plus b squared equals c squared, I know what you're trying to say. So whatever works best for you. Moving forward, part C, we're going to view this thing from the perspective of the 61-degree angle. From this perspective, x is the opposite leg, and the 30 is the adjacent leg. With opposite and adjacent, we're going to use the tangent ratio. So the tangent of 61 equals the length of the opposite leg over the adjacent leg. That's how we set this thing up. Multiply both sides by 30. And here we learn that 30 times the tangent of 61 equals x. Time for that calculator. 30 times the tangent of 61 degrees equals our x, 54.12. So it's approximately 54.12. We'll record our final response right up here. What tool did we use? Well, we used the tangent ratio. Again, if you just write tan, I'm okay with that. Just communicate to me which tool you used. That's what we're after. Part D. We have an angle, we have a side length, we're missing a side, we're using trig. We're going to view the thing from the perspective of the 72-degree angle. The opposite side here is our x, the hypotenuse is the 94. Which ratio do we use with opposite and hypotenuse? It looks to me like it's going to be sine. So the sine of 72 degrees equals the length of the opposite leg over the hypotenuse. So same process we just went through. Let's multiply both sides by the denominator. In this case, that is a length of 94. And I'm going to switch things up a little bit. I'm going to move the left side to the right side and the right side to the left side because I like the x on the left. So we know that 94 divided by 94 is 1, leaving us with x. That's the whole point of this move. 94 times the sine of 72 looks like this. Let's throw that value in our calculator. 94 times the sine of 72 degrees. I got 89.399. Oh, this is a funny one with rounding. This third 9 rounds this one up into a 10 effectively, which rounds this 3 up into a 4. So this one here would round to 89.40 or just 89.4. 89.4. And the tool that we used the sine ratio. Last one on this front page, part E. We're finding the the angle measure of theta. Remember, this is just a letter in the Greek alphabet, pronounced theta. It looks kind of like an Easter egg. If you really hate this, you can just cross it out and put an X there or something. It doesn't bother me. But keep in mind, it's just a variable. Treat it like a variable. So we're going to view the thing from the perspective of our theta, our unknown angle measure. We have the opposite leg over here, which is 15. We have the adjacent leg here, which is 10. Opposite and adjacent means we're going to do tangent. So we're going to set this thing up by saying the tan of theta, the tangent ratio from the perspective of angle theta, equals the length of the opposite leg divided by the length of the adjacent leg. Now, we're going to find the inverse tangent of both sides. When we do this, tangent and inverse tangent cancel one another out, leaving us with theta. And on the right-hand side, we have the inverse tangent of 15/10. Now it's calculator time. Remember, the inverse tangent, you need to press second and then your tangent button. Make sure the window has that tan, -1 up here, and 15 divided by 10. So here, theta is approximately 56.31. 56.31. And the tool that I used is the inverse tangent. You can write out the word inverse tangent. You can just write tan to the -1. I'm happy either way. I'm just looking for you to communicate the message here. A couple things I want to show you about this one. This next little interlude here is kind of for the nerds in the room. Notice how 15 and 10 are both divisible by 5. So 15 divided by 5 is 3, 10 divided by 5 is 2. So if I find the inverse tangent of 3 halves, if I just reduce the fraction that's here, check out what happens. The inverse tangent of 3 halves, well, we get the same exact thing. And that's not surprising. That's just a scaled version of the same triangle. So what happens here is we could have a smaller version of the same exact triangle, but it's got a scale factor of essentially 1/3 to what we have going on here. If this had a length of 2 and this had a length of 3, this angle measure would be the same. Because remember, the sine, cosine, tangent is just ratios. So it can help us find the missing pieces, but we're just working with a whole bunch of similar triangles here is what's going on. Okay, let's move to, one more thing I want to add with this one. I'm going to solve it, get the same exact response, but I'm going to use basically the formula that was on the board for the last, couple weeks. The stuff that was written in blue, it's since been erased. But I had this up there. It was theta equals the inverse tangent of the opposite leg over the adjacent leg. So this is a nice shortcut. If you wanted to start here, you totally could. Notice how it basically just skips that first step. So some folks like writing this down as a formula and you can just plug in the opposite and the adjacent. Some folks like setting it up just the way that we do all the other ones and then using this inverse tangent, kind of attacking it with algebra. Whatever you're more comfortable with, I'm cool with. Again, just to finish this one up, it's the inverse tangent. Well, the opposite leg from the perspective of tangent is the 15, and the adjacent leg is the 10. Notice how we ended up with the same thing here. I'm not going to put it in the calculator again. Okay, let's move to the back. We have one more question where it's just a triangle that I'm asking you to solve, and I'm not giving you the tool. This one here is going to be a special right triangle, and I could tell right away, and I want to point out why I could tell right away. If you end up with anything with like these radicals that's given to you, that should just scream to you, hey, this is a special right triangle. Let's look at the angle measures to see which one it is. Well, we know it's a right angle. All of these are going to be right triangles. The two special right triangles that we've worked with are 45, 45, 90, as well as 30, 60, 90. Well, we have a 60-degree angle, which would mean that this one must be 30 degrees. Remember the triangle sum theorem. All three angles must add up to 180. And always, in the right triangle, 90 of that space is already occupied. So 90 of the 180 is already taken, meaning that the two acute angles, the two other angles, must add up to 90. Well, 60 plus 30 is 90. So this is definitely one of the special right triangles. Now, here's where you just need your notes. I don't need you to memorize this. So this is the page of notes that I'm looking at right now. The 30, 60, 90 special right triangle is here. Here's the template that we created together. If you didn't, please do so now. This is super important. We know that if we have the short leg, no matter what it is, we can just double that value to get the hypotenuse. Well, in our problem, turns out we don't care about what the hypotenuse is, but just for funsies, I'm going to write it in. It's 2 times x. So whatever x is, we double it, and that's our hypotenuse. That's what the story that this tells us. Well, if we have that short leg, then we can multiply it by the square root of 3 to get the long leg. Okay, well, this is kind of funny because we have the long leg but not the short leg. So we can ask ourselves, what is multiplied by the square root of 3 to get the long leg? Well, hopefully it's pretty clear that it's 2. 2 is multiplied by the square root of 3 to get the long leg, which means that, again, looking at our template, what times the square root of 3 is the long leg? In this case, it's x. In our concrete example, it's 2. Well, x is the length of the short leg. So that means that x is 2. So x is 2. What tool did we use? Well, this is a 30, 60, 90 special right triangle. And that's it. There's no more work to be shown. We just used a template. That's the power of these special right triangles. They're not here to make you memorize more things. That'd be mean. The reason why I give you these special right triangles is because these are a giant shortcut. They're a cheat code. They make things move quickly. Now, with this one, you could have used some trig if you felt like it, if you just didn't recognize it was a special right triangle and you wanted to work harder, because you'd end up, some funky decimals, and you'd have to plug this into your calculator at some point in time. But you could view the triangle from here. You'd have the opposite, you'd have the adjacent. So tan of 60 equals this stuff over x, and you could solve it that way. I'm not going to walk through that because that's not the aim. I want you to work less hard. I want you to work smarter, not harder. So that sheet of notes that I showed you is what you're looking at. Now, on the actual exam, you might have a 45, 45, 90 special right. You might have one of these. You might have some of both. So you got to be aware of what you're looking for. Again, just for funsies here, the 45, 45, 90 is even easier because it turns out to be isosceles. Both the legs have the same length. To find the length of the hypotenuse, you take the leg length and just multiply it by the square root of 2. So those move a little bit quicker. Okay, down to the wordy problems. We're going to sketch and label a diagram, show your equations, round to the nearest hundredth, clearly label your answers. Okay, so we're going to draw some pictures here. The goal of drawing the pictures is to find some right triangle in there. We're going to use that right triangle and we're going to solve it basically just like every other problem we've already done. The only added portion of these is turning words into pictures, pictures into triangles. So here we go. Our friend Alice is flying a kite. She's holding the end of a 300-foot-long kite string, which makes a 37-degree angle with the ground. How far is the kite above the ground? Okay, cool. Let's draw a very perfect picture here. There's the ground. Here's our friend Alice. She is happy because she is flying a kite. Here is a kite string. Here is the kite. And it's got all the bows and things or something. It's a 300-foot-long kite string. And it makes a 37-degree angle with the ground. Okay, so this is kind of funny because we don't actually know how high Alice is holding the kite off the ground. So in a problem like this, sometimes it'll say, Alice is like, 5 foot 6 inches tall, and her hand when she's holding the kite is at 5 feet or something like that. In this case, we just don't have that information. So we're going to make an assumption here, and it's going to feel kind of funny, but we can only work with the information that we have. And the information that we have here is, that Alice is holding it. So I'm going to assume that she's holding it on the ground, at ground level. And I know that feels kind of awkward, and that's fair if you, totally fair if you feel that way. I feel that way too. But based on the information I have to make that assumption. I don't know how tall she is. Alice could be 100 feet tall. She's a mutant robot, something or other. Alice could be average height, 5'3", 5'4", whatever average height is. So I'm just going to operate as though she's holding the string on the ground. So I'm going to extend this as though she's holding it on the ground so I can make a nice triangle. And this angle is a 37-degree angle. So, and let's see what we're trying to find here. How far is the kite above the ground? Well, that is this length here. So this is our unknown that we are seeking. 300 is going to be our hypotenuse, and we're going to have a 37-degree angle. So the purpose, again, draw the picture to get the triangle. The triangle is what we care about here. So this is our unknown. This is a 37-degree angle, and we have a hypotenuse of 300 feet. So now we can solve this pretty quickly. We're going to view the thing from the perspective of the 37-degree angle. We have the opposite leg. We have the hypotenuse. This indicates that it's going to be sine. So sine of 37 equals the length of the opposite side divided by the length of the hypotenuse. Multiply both sides here by 300. And then we see, again, I'm going to flip the sides here. X equals 300 times the sine of 37 degrees. Then we ask our calculator so nicely, what is 300 times the sine of 37 degrees? And our calculator will kindly tell us that it is approximately 180.54, and well, that's the number that it gives us. In these examples, how far is it above the ground? Well, we're measuring in feet. I am going to be picky about the units of measure. Make sure to include feet. And this is like a kind of sort of a real life problem-ish. If you were, seeing a kite, like, oh, wow, that's a cool kite. How far is it above the ground? And your friend says 180.54. That's not a complete answer. You would look at them funny. Even if they said, it's like 200-ish, you would still look at them funny because you need a unit of measure here. Is it 200 inches, 200 feet, 200 miles, 200, I don't know, arms lengths, whatever. So if we indicate it as feet, that's a complete response to the problem. Okay, our final one. Here we go. A commercial passenger jet, we can just call that an airplane, takes off from PDX, Portland International Airport, will be flying directly over Mount Hood. Mount Hood is 2.45 miles tall. Okay, that's a mountain in miles tall. And it's 35 miles from the airport. After takeoff, air traffic control directs the pilot to climb at an angle of elevation of 6 degrees. Will the plane clear Mount Hood safely? If so, by how many miles? Okay, interesting. So let's draw a picture. Let's be very precise in our picture. Here is Mount Hood. It is 2.45 miles tall. So this length here, this distance, 2.45 miles. Over here, and that's the height. Okay, over here is where our airplane is. Let's draw the wings like this, then I'll draw the body like this. Yikes, turns out I'm bad at drawing airplanes. I'm just going to call that an airplane. And the airplane is taking off at Portland International Airport. This is PDX over here. It has an angle of elevation of 6 degrees. This length here is to indicate the flight path of the airplane. So it takes off here at an angle of elevation of 6 degrees. Presumably it's going to go over Mount Hood, so I'm going to draw this as though it is, and we'll find out if it actually is going to go over Mount Hood. Then the triangle that's being created, well, the height of Mount Hood happens here. So we are wondering, are we going to ever be in a position where we're directly above Mount Hood, or are we going to run into Mount Hood? That's kind of the question. I'm approaching this with optimism. I'm going to approach this as though we're going to make it. So I'm going to draw my triangle like this. But if we find out that this short leg is less than 2.45 miles, like if that's what we find out, then we ran into Mount Hood. That doesn't mean that we did the problem wrong. That just means that we answered the question. Will the plane clear Mount Hood safely? Well, potentially no. So that's what we're trying to figure out here. Well, what else do we know? We know Mount Hood, the height of Mount Hood. We're 35 miles from the airport. So we're going to say that this length here from where we took off to the height of Mount Hood, that's 35 miles. Okay. And then what we're trying to find here is the length of this short leg. So I'm going to refer to this as X. I know that's confusing because I called my airplane X. We're just going to change that, and all of a sudden we're going to call it A for airplane now. So the airplane takes off, angle of elevation of 6 degrees. Do we clear Mount Hood? Okay, the whole purpose of us drawing the picture is to get the triangle. Here's the triangle. We have a 6-degree angle where the airplane took off. We have an unknown distance here. We're hoping it's bigger than 2.45 so that we clear Mount Hood, but we'll find out. And then we have a 35-mile long length of this longer leg. Okay, let's find the length of X. We'll view the triangle from the 6-degree angle. X is our opposite side, opposite leg, and 35 is the adjacent leg. Opposite and adjacent is tangent. So the tangent of 6 equals the length of the opposite leg over the length of the adjacent leg. Well, now we're just solving it like all the other ones. Multiply by 35, multiply by 35. I'm going to flip the sides again. X equals 35 times the tangent of 6. Let's ask our calculator what that value is. Again, we're hoping, for the sake of airplanes and stuff, that the number we're about to get is bigger than 2.45. That's what we're hoping for. Let's see what happens. 35 times, but again, before we do this, type that in wrong, 35 times the tangent of 6. If we get something less than 2.45, that doesn't mean we did our math wrong. That just means the plane is going to crash into the mountain, which is, of course, a bummer. But good news is the math is just fine. So let's see what happens here. We're going to do 35 times the tangent of 6. We get 3.67. So X is approximately 3.6, more like 3.68. 3.68 is where we landed here. And this is how many miles. Okay, now we did find this missing length, yes, but we're not quite done, even though we put our unit of measure. So the question says, will the plane clear Mount Hood safely? So yes, plane clears Mount Hood. And then it says, if so, by how many miles? Okay, well, I'm going to put by blank miles. Let's figure out this number. Good news is it's pretty easy to figure out. So if this x, this red line here, is 3.68, and the height of Mount Hood is 2.45, well, let's just do 3.68 minus 2.45, and then we get 1.23. So we clear by 1.23 miles. So what I'm looking for in a final response is this. This is what I'd like to see in a box. I still need to see the rest of your work. I'm going to go through. Oh, boy, that wasn't all on camera. Okay, cool. Now it is. So yes, the plane clears Mount Hood by 1.23 miles, and this is what's in the box. Again, still need to see all the work. I'm going to look at it all, but I need you to put a box around your final response because that indicates to me you know where the finish line is. You know how to finish the problem. Really, that tells me that you read the end of the question here. There's 2 questions. Will it clear safely? Yes. If so, by how many miles? 1.23. I answered all the questions here. Okay, feel free to watch it again, pause, rewind, fast forward, skip, whatever it is you need. Next time you see me in class or in the hall or whatever, feel free to ask questions. This is the entire team test for the trig unit. You got this.